tutorial is to get emission factor. So, there are different categories I have already given in that. So, you can pick any 3 and go to the website that we had talked about, pick the emission factor for any 3 different pollutants. And then for those sources we do dispersion problem exercise. So, in the dispersion problem, I think before the dispersion problem I have one exercise on estimation of mixing length. So, here I think you have the mixing length, you have to determine so graphically, for example, you have to determine what is the temperature at the ground Tz at z equals 0 for the environment and T at z equals 0 for the pollutant. So, the environment temperature and there is a corresponding environmental lapse rate, and for the pollutant whatever temperature is, that is the adiabatic lapse rate. So, depending on, so in the problem itself I think you have to decide which is the environment starting point, lapse rate starting point, and which is the adiabatic lapse rate starting point. So, that I think we discussed in class. So, based on whatever the discussion we had, you can recall that. If you do not recall, just go back to the notes and read it, otherwise send me an email and I will help you at that time. Yeah. So, this is a calculation of the mixing length estimate. So, sometimes if the mixing length is infinite, then you say it is infinity, but in this case there will be a finite intersection somewhere. So, these will intersect somewhere and that will be the mixing height. So, you can do it either graphically or arithmetically, either way by equations. And this is the dry adiabatic lapse rate, and this is the environmental lapse rate, the mixing height based on that. The next is a dispersion exercise. So, you start with the full form of the Gaussian dispersion equation. So, the full form that we have is x, y, z and h. We have this full equation with reflection, and this example we did in class. You start with that and then reduce it. So, one of the things that I have asked in the problem is for a given set of conditions and for a certain stability class. So, you have to estimate the stability class for this particular problem. You have to calculate the what we are asking is rho a1 at some height. I think height I am asking is z equals to 1 or 2 or 2 meters or some such thing, as a function of x, which means that you have to calculate rho a1 x, y, z, h. So, along the center line, which means you have to calculate at 0, 2 meters and whatever is the height for different x values, which means you have to run this model for different x. You run it for x, so the dispersion coefficient will change with x. Okay. So, you can do it graphically and then you will get some relationship like this. So, typically you will see something like this. Yeah, the reason you do this, you see this is what happens is if there is a stack is very high and the plume is going like this, you will not see anything at ground level for some distance. Once the plume reaches the ground is when you start seeing some concentration. So, at this site there is nothing seen here, then it starts increasing. So, I want you to plot that. So, that is one exercise. This is a manual exercise. When you are doing air mod, this is done automatically by the software. Software will do 4000 points at one shot within 1 second. You can set it up like that to do in Excel also. provided you know equations for sigma y and sigma z. There are equations, mathematical equations. It is a little painful, but if you know for that stability class, you can take the points from the graph and fix a curve and then use that curve. So, automatically you do for one, you do for all of them. Okay. I think you can figure it out how to do it automatically. So, okay. So, that I would like you to try this on your own, and then after that if you have doubts, questions, how to do it, you are not unable to get any of these things. So, the emission factor that you get here, you I do not remember if the dispersion problem has a link to this first problem. The first problem, the emission factor is meant to be used in air mod. So, whatever you do here, you will do it in use that source in air mod, one of the sources in air mod, but you are free to choose this. But I think I have given you some number here for the q. This is q by some equation, right, to ux sigma y sigma z exponential whatever. So, this q is I think given, I have given this to you in the problem, I do not remember. So, you check that. Okay. So, I would like you to try this on your own. Sometime next week we can discuss this. So, before the quiz you have enough time to revise. So, quiz will be in class next to next Wednesday, 10 days on 30th, either in 355 or 356, one of those rooms. Okay. We will most likely in 355, we will assemble there and we will discuss that, decide that day. Previous day I will tell you. So, I want to continue our discussion in some application of what we were doing. So far to recap what we did mass transfer at interface. We first take the exchange between air and water. So, this is the simplest case for which we even derive the interfacial expression, air and water. So, the conditions for air and water, for example, this is a box model example we started with originally when we started doing the modeling, the description of the model. So, we are looking at exchange between air. So, for a simple case, so case 1, we look at evaporation of a pollutant from a lake. Okay. So, there is a lake and there is air . This is some volume and we are talking about this thing. Okay. So, this problem can be posed differently. The one way in which it can be posed is, let us say that this background concentration of A is in the air, rho A1 infinity is 0, which means there is no chemical A in the background air, and so there is a chemical. This scenario can be that somebody has spilled a lot of chemical here A, and this A is entering the water from the sediment, or somebody has dumped a lot of chemical into the lake and this lake is contaminated, and so on, different scenarios. So, the simplest scenario here is there is a concentration of A in the water, and so what are the implications of this? The questions that you can ask is the following. The first possibility is, what happens to A in the lake? First question. Is the concentration of A in the lake, how is it changing? So this problem, if you want to solve, we again write the mass balance, rate of accumulation. So, automatically when we ask this question in the lake, our system becomes a lake, the lake becomes a system. So, this volume of the lake is the system. So, for this system, rate of accumulation of A in the system equals rate in minus rate out. So, how can A come in? Rate of A coming in is, let us say somebody is constantly dumping stuff every day continuously. There is a pipeline coming in and disposing material here. Okay, so let us say there is a pipeline coming in disposing stuff here. So, you have Q into some concentration of rho A2 in, let us call it as in, minus rate out. What is this rate out? So, in this case several processes possibilities we can discuss. One rate out could be it is going into the sediment. We have not yet considered that. Let us for the time being ignore that part, status 1. So, we assume rate out is evaporation only, which means this is evaporation, rate out by evaporation only. So, you have to write this this statement in English first. This is very important because then from each term here. So, this conversion of the statement will be rate of change of A in the lake is a result of rate of A entering lake via disposal minus rate of A exiting the lake via evaporation.
So what if some person has dumped it just for once, like
Yeah.
one time,
Yeah.
and after that he didn't, nothing has happened. Then how do we consider rate in that situation?
Yeah, so that there will be no rate in, it will already be there, your initial condition will already be will exist. Your initial condition exists, even here that initial condition exists. So, I am going to remove one of these terms now. So, we are going to be assuming this first, there is no rate of entering, which means somebody has already dumped it. Okay. So, which means that there is an initial mass that is sitting there already, and that you have estimated it somehow, either by measurement or by estimation, that you know that 400 kilograms of some chemical has been dumped in. So, we have to link it back to our first problem that we did in this course, is mass balance. So, 400 kilograms are dumped in. What is the concentration at equilibrium in the water? The worst case scenario. That is the highest concentration of A in the water. That is your starting point. From there now, that problem was an equilibrium problem. So, now if that is happening, then after that we take that as starting point and emission starts from there, the release starts from there. So, we will take one by one. This problem can be as complicated as you want, and then corresponding to that the equation will change and the mathematics form will change. So, rate of change is, so now we are saying that rate of change is equal to rate of evaporation. Okay. So, you see a negative sign there, if this is 0, nothing is entering. So, because somebody has dumped already everything and this is a finite volume of dumping and nothing is entering, exiting. So, this becomes the rate of A exiting the lake. So, rate of change of this thing is dou rho A 2 by dou T into V of the lake of the water. So, every term in the mass balance as units of mass of A by T. So, therefore, V 2 into d rho A by dt is the rate of change of lake, because it is an unsteady state system, nothing is coming in. Okay. So, if somebody is putting material into it, if this second term, this term is not 0, there will be a term here. So, we will have it as rho A in constantly minus rate of evaporation. The rate of evaporation will be what here? This is the term now we have been discussing in the last few classes to fill up this term. Okay, this is the rate of evaporation term. So, the rate of evaporation is a flux into area. to area. So, the evaporation flux has units of ma by L square into T, area is L square, ma by T. Now, so this is evaporation flux. The evaporation flux is Na, okay. This Na has to be now computed. So, now we look at the system. There is water, there is air, and there is a concentration here. Now, it is going out from here to here. Concentration here is rho A to infinity, which we will assume to be 0 for the time being, no background concentration. When we say no background A in air, we are essentially saying this rho A1, sorry, rho A1 infinity is 0. This is the assumption we are making. Now, what do we write this term here? Now, first of all, you have to make this judgment whether it is a convective mass transfer or diffusive mass transfer. We have Na equals entire term. We have this term was V rho A plus Ja. We make the decision right here. Which one do you consider? If you are considering only Ja, how will you write the equation? Or if you are considering both, how will you write? So, what is the likelihood of this in this system? The information given to you, you have to, it is not sometimes enough for you to, so you have to make some assumptions here. Okay. So, if no information is given, you can do problems in multiple ways. So, let us make it easy on you for the time being. Let us say that the lake is very shallow and it is well mixed, one assumption. The water is well mixed. What will this immediately do? Water is well mixed means the concentration wherever in this region, everywhere the concentration is the same. So, well mixed essentially will make this into what is called as a CSTR, completely stirred tank reactor, which means that rho A2 is uniform throughout the volume, which also allows you to do this on the left hand side accumulation term, you can write it like that because it is uniform. Otherwise, you can't write it like that. You have to integrate that thing over the entire volume. Otherwise, you can't write V into d rho A2 by dt, it cannot be written. Okay. So, water is well mixed. Air is anyway moving. So, if water is well mixed, there is convection in the water and there is convection in the air. So, now we are assuming both, and we will say both convection plus diffusion. When we have convection and diffusion as a condition, then we use a convective mass transfer coefficient. We use a convective we will give this term called MTC, mass transfer coefficient, will write as MTC. I will write MTC henceforth. So, okay. Now, we have decided that, so which means there is a K mass transfer coefficient term multiplied by a driving force that needs to come here. So, we will start with the driving force. So, yesterday's last class we had discussed how we can write this flux term, and we have various options to doing it. So, in this particular scenario we are taking rho A2, which is a solution in the aqueous phase going into the vapor phase in the air. So, how many resistances are there? Is resistance are both water side and air side mass transfer resistances significant, which means can you neglect any of them? At this point of time you have no reason to neglect either of them. You do not have any information that can tell you that neglect any, because it is not pure chemical, you cannot neglect one of the phases. You have to consider the solution here and it is going across. So, there is an interface resistance here and this. So, both, the answer is no, both Ka21 and Ka12 are to be considered. Okay. Both are to be considered, then this term here will become, you can have two choices. You either have rho A2 minus rho A2 star or rho A1 star minus rho A1 infinity, either way. So, if you do this, we will do Ka2 1, we do this, we do Ka1 2. Okay. Is it clear? Anybody has a question on this? How we do this? So, we further write this, let us take the first one Ka2, because we already know rho A2, we need to do this in rho A2. Why? The other term that is there sitting in the accumulation, we can do it either way. So, let us take this first, how we can do this, rho A2 star. What is rho A2 star? Rho A2 is connected to rho A1, this is the equilibrium concentration, an equivalent concentration of rho A2, that is in equilibrium with whatever is there in the air. What is there in the air? 0. So, it is rho A1 by rho A2 star equals Henry's constant. So, which means rho A2 star equals rho A1 by Henry's constant. In this case, this rho A1 is rho A1 infinity by Henry's constant. Rho A1 infinity is 0, 0 by h is 0, 0. Therefore, this equation becomes Na2 equals Ka2 star into rho A2 minus 0. This is capital Ka2. Alternatively, you write the other term. If you write Ka, if you take Na equals Ka12 into rho A1 star minus rho A1 infinity, rho A1 star equals h into rho A2 based on this. In this case, it is rho A1 star divided by rho A2 equals h. We are now taking the equivalent concentration of A in the air, which is in equilibrium with whatever of A is there in the water. We are using the water concentration to find an equivalent equilibrium concentration in air. So, what we are doing is we are taking this entire thing and finding an imaginary concentration here that is in equilibrium with this mass, this concentration, and so we are calculating this one. In the other case we take this concentration and find out an equivalent concentration here, and we are taking this section. Okay. So, which means that Na will become Ka1 into h rho A2 minus 0. When you calculate, these two expressions are different. So, they will eventually become, they should give you the same value if you compute either way. Okay.